Hello, everyone. I hope you are all having a great day, and I hope you guys are excited for this workshop in the Explore Expander Bootcamp. Today, we will be having Lev from the Ethereum Foundation give his presentation on GKR Proof Recursion. So very exciting stuff. I'm just inviting him up on stage, and he should be here shortly to give the workshop. Hello.
Hello, everyone.
Hey. So whenever you're ready to share your screen and begin, the stage is all yours. Amazing. We can see your screen, so whenever you want to begin.
Yeah, cool. So I want to actually present sort of an open topic. So like I think right now status of this topic is that everybody understands that it's possible, but nobody actually have done this. So so something that could be built by I guess like anyone interested enough. So the idea of recursive GKR compression is that basically, well, okay, GKR verifier is quite large. And so idea is to compress it using like more GKR. And so you can actually did some math. You can count some Poseidons. So as an example, I will take Poseidon over BN scalar field, which is like the standard field for the curve used on Ethereum. Yeah, and by the way, can audience actually like, how do I check the chat or something? Okay, I see. So if you have any questions, please just ask them, because I do not have a lot of content. I am just trying to suggest something to build, and I want to have it as like more of an open-ended discussion. So like let's assume we have layers of degree 5. Then verifier's hashes will also take 5 elements. If you use like Green's optimization, I'm not sure if Green's optimization is actually used in Expander or not. But optimally, verifier's hashes will take 5 elements in some check. And Poseidon permutation with capacity 5 has 68 rounds. So if you have n Poseidons, you will have state of the size like 6n, and the amount of rounds is roughly 68 by logarithm of the state size. Okay, so if you want to do n Poseidons, this is the amount of rounds of GKR that you would need to do. So at some point, balance is achieved, at roughly 600 something Poseidons, we get into the situation when this number and this number coincide. So for smaller amount, verifier requires more Poseidons than you are doing in a proof. So question is like, can we compress it further? So if we use like naively use GKR, we cannot do it like we can do smaller than like roughly 500,000 Poseidons. Yeah, I'll check questions once again. Okay, it's just more GMs, GM, everyone. Okay, so we can also cut Poseidons into pieces. So idea is to commit to more intermediate elements and decrease the number of rounds. So you like cut Poseidon into like Poseidon permutation into 2 pieces, yeah, for example, you can make 2 half Poseidons, and then you will get a circuit with smaller verifier, which sounds okay. The plan is to do multiple rounds of compression. For example, you want to do like 10K Poseidons. You can move it to 1K, then to I guess 200, and maybe those Poseidons you already can do using HyperPlonk or whatever, like some bad proof system which doesn't, but with like less efficient proof system, but without with smaller verifier. Okay, and so question is, how do you achieve this? So some check verifier also does other things that are not Poseidons. For example, it evaluates polynomials and points, and it also does some algebraic expressions after the sum check have finished. So yeah, and my plan, yeah, maybe this is a question. Link to HackMD. It should be visible here, but I will copy it in the chat. Okay, there is the chat. It's very short, by the way. So like, once again, this is sort of a proposal of a project mostly. So ideally, we shouldn't use GKR, but we want to use something like HyperPlonk. So basically, this is a bit different from how Expander works, because in Expander, like your circuit is fully GKR circuit. And I think we should do something different. Basically, that we should have like this sort of like gluing board, which will be running HyperPlonk and handling control flow, and GKR will be applied to some commitments, to like some columns of this HyperPlonk. And I think it does not exist in Expander currently, but it probably can be added. So idea is that like you have columns that corresponds to like inputs of ith GKR protocol, and then verifier for this GKR protocol is done by the gluing board. And this gluing board allocates the hashes that it wants to do in ith GKR, in the verifier of ith GKR protocol to the CI+1. And so you're basically like deferring the operations to the next smaller GKR instance. I hope it makes some sense. If it doesn't, please ask something. But this is basically the way how you can do this. So you have like a single Plonk instance which handles the control flow, and like it does Poseidons up to GKR ith run of GKR being correct. And the verifier for the ith run of GKR is executed by the gluing board itself, with operations deferred to the next commitment. Yeah. So only difference between like normal Plonk will be that you will need to, like the verifier will need to parse the commitment CI and give it as an input to CI+1. So you are able to put it into the, like as a public input. So you are able to consume it into the hash. But yeah, this is basically the idea that I suggest. Yeah, so applications of this are numerous. I think it's very important to do this because, okay, maybe there are some questions. Okay, no, there is another GM. Hi. So applications are like on-chain wrappers for GKR and for Stark. So currently this is an extremely large bottleneck. Like Starks are typically wrapped into like gross 16 proofs, and this is really not efficient. It's inefficient. It's so inefficient that people typically need a large server to make a Stark proof, and this would allow I think this approach should allow to make on-chain verifiers that you can run this wrapping on a small phone, on a good phone, on maybe on a decent, even like a mid-level laptop. So for Starks, it's a bit more involved because it also involves some amount of arithmetic, but generally most of work that is done in the Stark is hashing. So clearly you should be able to do the same paradigm. Like basically this first 10K Poseidons will be from Stark, and then you will be like compressing them with GKR. Okay. And another interesting thing is this is probably one of the easiest ways of adding zero knowledge to GKR, because while we sort of liberally call all these protocols ZK, they're not actually zero knowledge. And yeah, okay, I will check chat once again. Yeah, server specs usually for Stark that you have mentioned. I remember. I will find them for you, but it was something quite insane. Maybe it was. I remember like very. I can find it later, but maybe it's not a like I think decent server should be able to do it. Like even top end Apple laptop manages to do it, but it takes a lot of time, and like we want these systems to be available on phones or like relatively old laptops, not like top end machines, yeah, the size of the Stark proof is even larger than GKR. GKR is typically in like hundreds or thousands, and Stark is like, I don't know, 10,000. Maybe slightly less, maybe Steer is slightly less. But the point is doing it on chain directly is not a good idea. And yeah, one of the way of fixing it is by wrapping. Okay, and this is one of the easiest way of adding ZK to GKR, because like basically GKR like leaks a lot of information about your polynomials, and because it exposes so much like sums over some subsets, and so like if you are doing this wrapping, then some check data is not actually exposed because your run of the sum check is hidden inside of the snark, and so amount of like blinding elements that you will need to add is likely much smaller. Okay, and there are some challenges which are like, some of this is just me not being too familiar with Expander. I have spent a lot of time like dealing with GKR in general, but Expander system might like I did not do it with Expander concretely. So I think that integration with Expander might be hard because you need to interoperate with the gluing board, with this Plonkish layer. And I think using Expander's way of control flow is likely in GMI. Yeah, realistically, what's the biggest constraint to running on a microwave? Haha. Well, the biggest constraint, okay, so allegedly Bootcamp is about Expander, which is a proof system, GKR, like proof system, like front end for GKR developed by Polyhedra. So ideally you should be able to like add it to Expander, though it might be a bit hard. So one of the things that Expander lacks is I think it does not have this Plonk layer. So you would need to somehow integrate it if you want to use Expander. And Expander's way of control flow is doing it inside of GKR itself, and I think it will not work for this. And another thing that you would need some intermediate representation for GKR verifier. So you can then make a proof for it. And it likely involves arithmetic operations, hashes, and nothing else. So basically, you would need to compile GKR verifier into this intermediate representation. And then compile this intermediate representation back to GKR circuit. And so annoyingly, GKR sometimes hashes different amounts of data. So inside of the sum check, we always hash our polynomials which have fixed degree, for example, 6 or 5 if you use green streak. But there are prover messages outside of sum check at the start of the round and at the end of the round. This will, like, I think most simplest way of doing it is to simulate it using fixed fun in Poseidon. So for example, if you need to hash, I don't know, 4 elements, you like hash 6 elements instead, but you hash 2 additional zeros or something like this. So this is just a bit annoying. Basically, verifier will need to hack a bit so it aligns with this form. Basically exactly out of the Gleaning board might be hard to get. So like naturally, I would suggest using some circuit builder, maybe Halo 2 or something like this, and plugging in GKR as a component which acts on some columns. So this is like how I envision this working. Okay. And this is pretty much the plan that I want to suggest to work on. And now I would read some more questions. Well, you should read the documents to ZKML, folks. Okay. Okay, this question seems unrelated to my talk, but I will answer them anyway. So. Yeah, okay, but if you have any questions about like actual content of my talk, please ask them too. So comparing to ZKML, ZKML folks sometimes use GKR for lookups specifically. Expander proof system tries to use GKR as a general purpose proof system. And one of the things that GKR is really good at is doing very data parallel circuits. For example, if you are doing a lot of hashes, it's a nice idea to do a lot of hashes in parallel by using GKR. And coincidentally, its verifier also involves a lot of hashes, which leads us to this idea of recursive compression. Okay, so I'm not sure. Yeah, okay, I think I don't want to. I will stop screen sharing and like, okay, I want to have some sort of open-ended discussion on this because as far as I understand, this is like basically one of the topics that you might choose as like potentially doing during the bootcamp. So like if you have any questions maybe and consider doing this, okay. GKR is efficient when the circuit size is much larger than the circuit input. There are various measures of efficiency. So GKR is in general does not require you to commit to intermediate values. So this is always an advantage. Yeah, okay. So you didn't have an introduction on Expander, then like I would write a bit larger introduction to GKR and Expander then. I'm surprised. I thought bootcamp was going for already some time, and so I expected some level of knowledge about GKR. So GKR is it does not commit to intermediate elements, and so in that sense, like from prover standpoint, is always somewhat faster than proof systems that need to commit to intermediate elements. But it has an issue, which is verifier size. And verifier size increases if your circuit is not data parallel. So if your circuit is doing some arbitrary stuff, like imagine like ZKML, I don't know, like it's doing some like randomly gluing some variables to some other variables, then you probably will not be able to get a small verifier for it. But for data parallel circuits, verifier is very efficient. Arguably, it's even more efficient than I mean, amount of hashes that it does is like smaller than a typical Stark. Okay. Okay, are there any questions about like recursive compression? Yeah, okay. Yeah, this makes sense. So when people typically talk about recursion, they talk about, so I'm answering how GKR recursion compares to other schemes. So first of all, you can also do like full recursion. What I'm suggesting is not a full recursion. It's like taking a single GKR proof and compressing the part of this proof which corresponds to the sum check. And like when people typically talk about recursion, they talk about like, I'd say they typically talk about full recursion. So you are taking a proof and verifying it inside of other proof. You can do this in GKR. And there is a limit. There is a limit how much you can do it. Actually, this is, I have written it in the first slide. So let me try to pull it up once again. So as you can see on the first slide, or one of the first slides, so basically, imagine you like bulk of work for GKR is doing like some amount of Poseidons. So if you want to do n Poseidons, you need to spend roughly this amount of Poseidons and verifier. So for n larger than 700, you will not be getting smaller proof than the one you started with. So I would say it's like it's good for a prover, but it does not allow you, like without like if you're not doing this trick with cutting, you will not be getting like small proofs. But in terms of like just recursion, I think it's okay. You can use GKR to run GKR. Well, recursion is when you are trying to verify a snark inside of the other snark. People are using various tricks for this. Like the thing that you are mentioning, like the cycle of elliptic curves, is basically about commitment schemes. GKR uses a commitment scheme in the end. It can be any commitment scheme that you like. And the scheme that I'm suggesting is not a full recursion because it does not compress the opening of the commitment. It only compresses the part of the rest of the protocol, which only involves hashes, and so it does not require a cycle of curves to process. But in general, recursion is when you put verifier into a snark, and yes, cycle of curves is one of the ways of doing it. Yeah, I can comment how recursion compares with folding. So basically, you have two parts. Two parts are like polynomial interactive oracle proof. It's called PIOP. And in case of GKR, like GKR is actually a polynomial interactive oracle proof. It's not a full proof system. And the second part is a commitment scheme. And folding is a thing that works on commitments. So basically, it allows you to reduce two statements about commitments to a single statement about commitments. But you still need to run some part of PIOP. So I would say that this method can be combined with folding in the sense that you will need to run GKR recursively, but you then can fold the commitment. Yeah, this is another way of looking. Well, everything that we're talking about uses fiat Shamir. Like literally everything. Like all of the system use non-interactive snarks. Yeah, I know it sounds funny from a person who just like published a paper about vulnerabilities in fiat Shamir, but indeed all of the systems do use fiat Shamir. So folding is preprocessing for snarks. Snark is heavy machinery. No, folding is a weaker version of recursion. It's like a way of like doing some parts of the recursion, like instead of doing full recursion, running full opening for a commitment scheme, you are instead reducing two openings to one. And this somehow is cheaper. Link to paper, please. Find it on Twitter. It's called How to Prove False Statements. I'm sorry. Yeah. Okay.
Great. Lev, I just want to say thank you very much for your presentation and discussion. And guys, please do continue putting in questions in the chat.
Yeah, folding is based on additive homomorphism. Actually, like the system that I'm suggesting also probably uses elliptic curve-based commitments because it's kind of pointless. Like only real alternative that we have to folding-based, to elliptic curve-based commitments right now is commitments based on hashes, like Starks, and I mean Fry. And they involve, like their verifier just involves more hashes than GKR. So there is no point in compressing GKR if your opening is like your commitment scheme already requires much more hashes. So, and they also cost a lot to do on chain. So a reasonable way of doing them on chain is like using elliptic curve based commitments. At least now. Maybe later we will have more on-chain primitives, I hope so. But right now we don't. Oh, hi Rajesh. Rajesh is typing something. Yeah, okay. Well, I don't have much. This is just a proposal that's something that should be done. So we initially wanted to like do it inside of PSC, but apparently we're either too lazy or too busy, and so I decided to sort of suggest it to general public. Maybe somebody can pick it up. What kind of this is irrelevant. I'm sorry. I will answer it if like witness instance pair are folded using linear combination. Yes, yes. Basically, like if you imagine when snarks on mainnet 4 years ago already, they are already on mainnet. What kind of primitives do you hope to see on chain soon? No, I won't answer that. And all the questions are about folding for some reason when I did not mention folding even once. But yes, witness instance pairs are folded using linear combinations. In general, if you want to, there is actually an interesting paper about folding. It's called recent paper. Let me find it. There is a recent paper, folding everything. Folding Srinath's. Yes, I will give you the link in the chat. If you are interested in folding and also interested in GKR, there is a recent paper. It's of course also Nova teamed. It's called neutron nova and neutron nova, and it is like some way of folding GKR. So maybe if you're interested in GKR and also in folding, maybe you should consider reading this. Yeah. Okay. So I guess then we will return to snark compression, the GKR compression, when we get more insights about GKR. So this was kind of short, but anyway, thanks for listening, and have a good day.
Yeah. Thank you very much, Lev.
Highlight what was okay. There are actually other questions. The snarks are already native in F. We have pairings. We could have more primitives, yes. But we have pairings already. Yeah, can you give us a highlight of what was found and fixed on Expander? Actually, what was found was that if GKR circuits are very large, then you can make an exploit and attack them. It was not an issue in Expander, it's an issue in the protocol itself. Like Fiat Shamir becomes weak if your GKR circuit is very large. The idea is that circuit is able to compute the challenge that will be given by the Fiat Shamir verifier, and then all the scheme breaks. And so the fix that was applied to Expander was just, if your circuit is very large, maybe you artificially increase the size of the verifier a bit, so it still cannot express the verifier. So yeah, something like this. Okay, I guess we are like finishing a bit early, but still.
Yeah, no,
yeah,
it was
thank
a
you.
great discussion. And thank you for sharing the slides as well. And thank you everyone for asking such interesting questions.
Sure. See you.
Yeah, if anyone has any other questions, pop them in the chat now. This will be recorded and uploaded and put in the Hacker Pack tomorrow, so you will have access to that. If there aren't any more questions, which is also totally fine, Lev, thank you very much for being here and for your interesting proposal. And thank you everyone for such a good discussion. And I hope you all have a great day. And we'll see you at the next workshop. Amazing.
See you.
Bye.